So next up, we have Grant Babb, and I realize he's actually a local, and I don't want to imply that he worked any less hard to get here just because he's physically closer than Jan. But Grant works for Intel as a cybersecurity researcher there, and we'll be talking about actually several sort of intermediate models, transformations that are useful in doing analysis of Netflow, and he can tell you more in a moment. So some clapping from local.
Do I have a clicker? Forward, back, okay. Welcome, everyone. I feel like I owe everybody here a standing ovation for sticking around to the very end of the conference. You rock. Despite my title, I am not an academic. I just play one on TV. I am an analyst. I just have obtained some advanced degrees, but I have a passion for data and telling the story. And let's face it, catching bad guys. So I found that there was more that we could do with the technology that was evolving, and that's kind of what I wanted to show you today. I'm going to not spend a lot of time on the first two questions, because that's really preaching to the choir at this conference. I think we know why Netflows already. But I definitely want to inform you on why you might want to transform them into new structures for analysis and what analytics might be brought to bear on this. So I say this is a big question, is you want to find these patterns in my network flow data that might be potential security threats. But maybe we also think outside that the big question is the fact that there's a whole lot of Netflows. So the answer involves looking through billions and billions of Netflows and being able to analyze them at scale. Also, Netflows are, we think, critical to this kind of middle ground between having to have every packet that went through your network available for analysis on up to the current problem that kind of exists with security events that, we only know what the security event tells us. We don't know what happened before that. We don't know what happened after that. So this telemetry that Netflow can provide is a very valuable thing. And it also gives us kind of a trigger to go back down and pick up stuff in the packet stream whenever we need that information. Also, besides the data size, it represents kind of a middle ground in terms of ease of analysis, but not that easy. So, in a regular environment, your external Netflows can be in the billions. You add internal, doubles that, triples that, quadruples that. I mean, this is a lot of data that we're talking about. So we've seen previous research, both at FloCon and in other publications, about the value of looking at Netflows as a time series, right? It's this IP was talking to this IP address, and different stuff happens over time. There's a lot of well-proven analytics that work when you can use Netflows as a time series, but what do we know about Netflows? A, they're usually unidirectional, kind of a problem there. And if you want to create them and turn them into this two-dimensional structure like this, then it's kind of an M-squared operation. For those of you that don't know that intrinsically, that's a fail. Simply, there aren't enough computers in the world to make it worthwhile doing that. So we looked at how do we pose this Netflow problem, make these things into a matrix where we know there's a lot of cool things we can do with them, but also get past this, these initial fail conditions. So this is just the schematic. There will be no quiz on this later, I promise. Over here, you have your traditional kind of Netflow idea. What we did is we thought of the rows as a channel. We had a lot of graph discussions here. That's like an edge. This IP address talked to this IP address. And what we thought of is that when IP address A talks to IP address B, that's like a positive flow. When IP address B talks to A, that's like a negative flow. So you have some idea of like the bidirectionality. So you now have biflows that their time behavior is based in here. So here we have like each minute in the day. So basically that ends up being kind of an up and down kind of signal that you get, which motivates a whole lot more analysis. Now, how do we get to this? Because as I said, it's potentially an M-squared operation because you have to compare every IP address to every IP address, see if you found it before, et cetera. Well, we took advantage of the natural state of IP address networks, right? Is it not all the IP addresses are used? And over time, it's not like you keep, the number of IP addresses isn't random. It doesn't keep growing linearly, right? I mean, a lot of people might go to Google. That's probably going to persist over each time. I mean, there's not going to be a whole new billion IP addresses that show up on your network that were never there before. Or if you do, you got a whole different problem, right? So what we did in this algorithm is we basically take the IPs that are common on the network, and we, in order to be able to scale this algorithm, we have to be able to parallel it. Like this is done on 8 node, 16 node clusters, and we have to distribute that workload evenly across all of them, or else this is another fail. If all the work goes to one node, then what was the point of the other 15, right? So what this does is it takes the IP address and it partitions the address space, which is very awkward in the IP world because it's not even at all. And it puts it into something that can then be divided evenly. This was a very important piece, and I found out my conventional wisdom is if it takes 2 pages of tiny text to explain something, it's probably a patent. So I will not spend the time to explain that entire thing, but basically this is what it does, is we create even buckets for all the IP information so that we could process it evenly. For those of you that, I'll tell you why you might care about this. Up here is really what a normal IP address space looks like. Like if you look at the IP addresses you visit, that huge spike in the, 10 to the 4, the tens of thousands, that's the general, that's the internet basically, like where most of the internet traffic's coming from. And you notice there's a few other spikes, but mostly it's pretty sparse and barren in there. So we can take advantage of that. Our thing basically takes this horrible nightmare of a CDF over here on the right. I mean, how do you divide a vertical line into 10 even parts horizontally, right? I mean, it just isn't going to happen, right? So what we do is we basically figure out a way to partition it into as many workers as you need to. Down here, we have several thousand workers, but if you notice, we're down to 120 being the biggest size. So this means that we can easily do operations like sorting them and copying them and manipulating them and everything else because we've broken a huge problem into a very small problem. We're talking about 4 billion rows a day that basically we can say, each worker is only going to have this many and we can guarantee it, which gives you this nice smooth CDF on the other side. So to an operational person, it means that you can get your data into this format. For those of you that need a little more demonstration, this is just the support of what we did. Is that as you keep processing more and more records, what we see is that this combination of searches we do, and we have a draft publication I'll be happy to share with anyone that wants the details. We're able to force the complexity down to n log n, or right about that point, which is that's a pass. That's something you can do. That means you can run multiple processes at the same time. You can predict how big they're going to get, et cetera. The problem's not going to blow up on you. And if you just see at the bottom, that's just an idea so everybody knows what a logarithmic curve is. At the top, we have the actual intersecting a bit with what we predicted, and we got pretty close. So now that we know we can transfer this stuff, we can actually pull this off. We can divide this into as many workloads as we need to, so it doesn't matter how big the problem is, we can tackle it. What are we going to do with it? And that just gets the data to us. So there's a variety of analytic approaches. I think we all know that with the complexity of NetFlow data has been demonstrated here, not all of these problems are nails, right? So we don't need just one hammer to solve the problem. And we've seen examples of network analysis, but we also don't want to give up on things like pattern analysis because their spatial patterns exist over time. Like where, an IP network has meaning like in the geolocation where it is. It also has meaning in terms of what the roles of these things are. I mean, there's important patterns that exist there, but there's also important patterns that exist in space. We all know what low and slow is, right? So the fact of something happening in 5 seconds, or I think I heard some great examples about machine time versus human time. Time scales and the way stuff evolves over time is just as important, and there's meaningful patterns there. And certainly, let's not forget that we are visual creatures, right? We have to be able to pass these back and forth into visualizations and illustrations of what we're doing, so that not only do we make sure that we're not just making a huge mistake, but we're also communicating stuff without expecting people to have to understand every single thing that calculation we went through. So in this solution approach, one of the things we found that can take a whole lot of data and provide some meaningful results with Netflows is a technique called Latent Dirichlet Allocation. You'll hear me call it LDA from now on, because that's too many syllables for me. Excuse me. So what we did was, basically this is some way people might call it a clustering algorithm, but it's a little more unique than that, I think. Normally what it's used for is that you have these words that exist, and there's documents that have different collections of words. And the idea is that you go through this algorithm, and it kind of gives you an idea what topic they might belong to. So it's something used often with text processing, or just try to classify different kind of documents that might have one or more different kinds of words in them or keywords in them. We hacked that algorithm, and instead we thought of each of the ports that communicate on as a different conversation. 80 is like a web conversation. 25 is mail. 22 is SSH, et cetera. So based on these well-known ports, we thought of those as our topics, right? And so we wanted to, or our documents, excuse me. And so then we wanted to take various parts of the communication, the packets, bytes, et cetera, as the words, and to see what it could tell us. And there's the best part of the algorithms and the approaches I've showed you is that there's different ways to ask these questions, so you get slightly different answers. So the flexibility is, I think, what appealed to us the most about these. In this case, what I'm going to share next really has to do with the idea of the port that's coming in on a destination IP. That's usually like a well-known port, right? I mean, if you think of most of the I'm requesting stuff from a web server, right? It's always going to come in on port 80 if it's a web server, et cetera. So we really focus on that because that was the most meaningful data set for ports, the meaningful range for ports. And so here's an example result. This was actually on the vast data set, so it can be reproduced, and we'd certainly always be interested in any corroboration or collaboration on that. So our question was, what are the strongest matches for automated communication? Because that's something that you want to look for in your network, right? Sometimes it might be fully expected and normal, but within that communication, you want to see if there's anything abnormal. And so one of the results here is you get 7 different ports. There's 7 different numbers up there. But what the algorithm has done is it said this belongs to all the guys in dark blue. They all belong to the same topic. They're considered kind of similar. And for those of you ops folks out there, you can probably quickly see this kind of has a lot to do with file sharing. And NetBIOS, all that kind of stuff, all that little handshake you have to do to like connect to different servers in a network. And you would not expect that maybe the SSH and the NTP communication would necessarily be the same kind of conversation. So intuitively, you already see there's a little support for what's going on here. Does anybody know what 587 is? Just as a... Yep, exactly. It's like Gmail, basically. So what we show here is something for the analysts. Out of this big pile of data, hey, you have like 7 leads to follow up on. So our real focus has been how do we solve that problem, right? Is we didn't know which ports might have kind of automated communication on them rather than just going and searching for each one individually. And we used machine learning to try to keep the analyst sharp, to do a lot of those queries and all that number crunching so that whenever they get to the information, they're faced with a much smaller thing to investigate, and they can focus more on the interpretation stage. So we have a demo that I'm happy to share with folks. Just get with me after the meeting. We can set up a time to meet. Where basically you can go through each one of these, go back, query the data, and you're able to actually realize, like with port 123, if there's an automated attack on that port, that's actually detectable with this approach. So moving on to another analysis technique, there's something called, I actually think I just saw it in the last slide, is something called principal component analysis. It's a very deep field, but basically it's something that gets used in tons of disciplines. It has high value. It's used almost routinely. So our approach is that's what's good enough for climatology and neurology is probably good enough for security as well. We have seen that proven out. So the thing that I would share that's most valuable about principal component analysis is it takes that matrix format that I explained, and it decomposes things so you get patterns in space and you get patterns in time. The example that I use below is with a lot of climate data. That's a map of the Pacific Ocean. I realize that may be not something everybody picks up on with this group, but for those of you that live on the West Coast, that's the Pacific Ocean. And it takes a lot of climate data, and it says the overwhelming pattern here is focused in this particular area. And for those of you that kind of know a little bit about that, that's where El Nino is. And at the same time, you see over here that the time component that's pulled out as the dominant pattern corresponds almost exactly to El Nino as well. So our research has been in taking these kind of patterns, but furnishing the analysts with the tools they need to interpret it. This isn't easy, right? And with PCA, the biggest challenge is being able to interpret the data. And I'll share with you a lot of what we've done in visual analytics to support that. So one example of the PCA results is that you get back these big matrices of numbers, which are not so helpful, right? And so one of the things that we did is we played with creating a communication matrix, whereas all the source IPs on one axis and all the destination IPs on another. And that's part of the way is just to be able to understand where the numbers lie, et cetera. But what we also found is that visually it really helps you understand what normal is and not normal in your network. In this particular example, you see kind of a vertical bar off to the right. Well, if you had seen if you look at other normal depictions of this network, you don't see it all sitting there by itself. There's if you notice over here on the left, this is all internet traffic, and you see kind of an unbroken line. Well, what happens is that somebody is going out from a single source IP, and they're looking at a bunch of destination IPs, but those destination IPs aren't doing anything else, AKA they don't exist. So this is one technique, and that's useful for detecting automated broad-based scanning attacks, which there's a lot of ways to do that today, I know, but this can be on any time scale, remember? This could be over 3 days if you had the data, but the pattern's still going to emerge without the time component. And what's most important about these kind of patterns is that once you take them, they're just numbers, right? Our system, our solution, gives you the ability to go back and search for those patterns in the future. So once you find a pattern, it's not up to you to keep finding the same pattern over and over again. You should then be able to find that pattern automatically. At least that would be my passion and my dream as an analyst. Maybe some of you like doing the same thing over and over again, but not me. So another technique that met the criteria we wanted, which was, is it scalable? Is it fast? Is it something that can be interpreted somewhat easily? I mean, we can pick a lot of algorithms that require several PhDs to be able to understand. That's not going to really be helpful to the standard ops person, right? They need to be able to understand what it's telling them, and they need to be able to respond to it. Fast Fourier transforms are one of those things that are great to build on, because what they do is it's a foundation of radar, foundation of a lot of telemetry, right? It takes information from the time domain and it throws it up into a frequency domain. Why should you care about that as an ops person? There's a whole lot of problems that are really hard to think about otherwise. Things like, what are normal working hours in my company? Like, how do I find the stuff that's outside of normal working hours? Well, if you think about it, when it starts and when the day starts and when the day it ends, that's a periodic pattern, right? And you can use that as a filter. Similarly, this whole low and slow activity, right? Something that's happening all day long. It's still happening with some kind of frequency. So you have these examples, I guess, to kind of help motivate and bring that home. So here we have a couple of what we call about channels. There's an IP address talking to another IP address. And if you notice, sometimes the communication goes two ways. But if you look at the top example, you have, excuse me, you have a behavior that's happening all day long. This is like over 24 hours. If you think of what an IPS would normally detect, this would not be it, right? Because it's not looking at a 24-hour window of data. So here we have something that's going out, and it's just doing a really small amount of data downloaded or uploaded. It's only about 100 bytes or something like that. So very small, very low, and very slow because it's happening over the whole day. However, if you look at the fast Fourier transform, the power distribution, it's saying where the frequencies are, looks a lot different than the one below it, right? You see that there's a whole lot of repeated behavior, a lot of cycles of stuff that are going on. And again, the expectation is that you wouldn't look for these, is that you can easily turn this into a numerical pattern that you think can then go search about other data. And why would this be valuable? Well, I didn't have to tell you the port. I didn't have to tell you the IP address. You didn't have to have any of that information to go out and look for this kind of automated behavior. You can just say, give me something that kind of closely matches this power distribution, and it doesn't matter what port or what IP address it's on. So a little more difficult maybe to interpret in some cases or to get to that point, but once you have these signatures, they're golden. Okay, so I covered the patterns, signal, graph analysis, et cetera. I think what we all find is that these, while they may be powerful, you come up short at some point in terms of your ability to explain them or to be able to explain somebody who is in a leadership position or some other place, why they should care, what they need to do about it. And that's really the end product of an analyst, right, is we have to motivate some kind of change. We have to get a decision made. This is where the visual analytics is key. We use, for those of you who are familiar with D3, it's an interactive visualization platform. I found that the best charts are ones that you can interact with and move around. It keeps your brain working, but also it's very easy in this case where you're trying to show that all of the hosts in a network are normally communicating with this one time server, but you got two guys in the brown and black that are doing something completely different. That is something that can be picked up by a non-technical person we find quite quickly. And there's a lot of value in that. So just to walk through that example more slowly, what you see here is, I don't know if you've ever seen a chord diagram before, but we're big fans of it when it comes to flows. Each of those bands is an IP address talking to another IP address. And the size of it, that has to depend on that's like how much traffic. That's the number of bytes. And so in the 1, 2, 3, the NTP port example that I talked about investigating before, you normally expect everybody to sync in their watch to the same clock, right, on a network? Well, so what you would expect is this yellow pattern here where all the IP addresses are talking to one IP address to get their time. But I think anybody can see that there's two guys that are doing their own thing, right? They're going somewhere else. And so that's enough, that's a very clear visual picture that, I can show you the same amount of text data and you'll get to it a lot quicker this way. So getting through your analytics text faster, but also being able to communicate to other people is key. I like to use the phrase I don't want to get myself lost while I'm doing this, but I really don't want to get my boss lost, right? So what we're focused on is trying to enable both. A brief thing about IPython for those of that aren't aren't from the academic field. Python is our glue for all this stuff. We use things like Hadoop. We use a graph processor. We use Spark, a lot of different pieces. But Python, besides being a great glue, it also offers this notebook format, which all of our solution content is in scripts on the back end, but it's also something that you can take and put into this notebook. You can document, annotate, and basically outline your work product, which is not only important for being able to, so you can remember what you were doing later, but also for the senior people in here to be able to pass down what they know to the junior people. Completed scripts, we believe, are something that can be handed off to first-level SOC people without a lot of issues. And also, you can take workflows that work, modify them, et cetera. We find that most people really prefer that approach to just sitting down at the dev environment and like coding their whole thing. Now, I'm sure there's people here who would fall outside that, but our target is security people. And we believe that teaching data science to security people is easier than teaching security to data scientist people. It's probably because there's like a little gene or some kind of defect that makes us security people, that makes us so passionate about such a really complicated domain. But giving you the tools to make your job faster and easier and more effective, it's a pretty easy sell, right? So again, thank you so much for all your time. We do have a publication of this that explains all the techniques in detail as well as the algorithm. I've included a couple of basic resources about if you're more interested in FFT or PCA or something. I mean, there's some sort of really great works that introduce you to it, and including LDA. There's also some great, plenty of open source links, and also some support for why we think this can happen, which in case I have to defend that in the time that I have. Any questions? Besides, when do we get to leave? Which is pretty soon, I'll bet.
I didn't catch what matrix you ran the PCA on. Which matrix was that?
Oh, yeah, thank you. That was the IP channel to time series matrix. But the beauty of PCA is that we could have done it against any two variables that we chose. Like we could say all the IP addresses against port, IP addresses against time of service, time of service values. I mean, there are several that I think we plan to include, but the research I've shared with you today is based on trying to show why it was really cool that we went to all that trouble to create those time series matrix, and PCA was the best way to show the patterns in time and space.
Okay, and what kind of patterns did you detect using PCA?
PCA has a tendency it's supposed to, at least from its invention, was supposed to identify sort of hidden factors in the data, right? Mm-hmm. And generally, what we see is the first mode is almost always top talkers. Mm-hmm. You look a little further and you might see the ones that communicated with the most hosts or that communicated over the longest time. The interpretation varies with each data set, and our biggest focus has been on how we can easily interpret that. But generally, we've identified different business-to-business systems that have a very interesting kind of communication pattern. It's very different from everything else. So it's, to your point, it's mostly outlier detection. But I believe that our next area of research is going to be how we just keep chopping and filtering it down so that we get more and more interesting patterns that result, so that it's not the most obvious stuff that comes to the top. It's the stuff that maybe might be the most interesting or the most insightful. That's a great question.
Okay, thanks.
Sorry, it's so bright up here. I can't see anybody anymore.
I was kind of curious how, with some of these fancier techniques, sometimes you run into things like singular matrices or something, and it just sort of barfs on you. And so I'm just curious, when you were talking about feeding in lots of different things, how much data, not smoothing, but how much did you have to get the data, format the data and get it and clean it up before you threw into these things, or did you just sort of throw it in and then see what happened, kind of a thing?
We did not have to do, I'd probably say if we had some false, obviously any knotted numbers or any of that is completely impossible in this context. I don't think we actually had to do much. I haven't seen the matrices. You mentioned singular values, singular matrices. This is if it's ill-conditioned, there's sometimes that the numbers can be so far out of whack that you really can't believe anything you get out of it. I think where we're lucky is that these are all whole big numbers, hundreds of bytes or millions of bytes. So the there's not a lot of decimal points or a lot of wide range of values. Demeaning it probably keeps us out of trouble. Like if we just, so I would say that the scaling and demeaning and the fact that it makes sense as bytes and everything is probably our best bet. If we probably monkey too much with the data, we would probably run into exactly what you're saying. And we'll probably will sometime this year for sure. Again, great question.
First of all, nice presentation. I definitely want to see the demo.
Okay.
And as I understand it, your channels are unidirectional, so that for any pair of addresses, there will be 2 channels, one in each direction.
They're bidirectional in the sense that all the communication between those 2 IP addresses is captured in that row.
Okay, so both directions?
Yes, both directions. So one direction is going to be a positive value, the other direction is going to be a negative
okay.
value.
I forgot that part.
Yeah.
Okay, thank you.
Sure. All right. Thank you.